In one of our first examples, we had shown that the language that consists of only zeros and ones or A's and B's, whatever it might be, any one string for which the string has equal numbers of symbols one after the other, meaning that there's equal numbers of A's and then an equal number of B's. Like you can't, any language like that isn't regular, right? Well, I want to show you an example of a language for which those strings are contained within another language that is a broader one. And then ultimately I want to answer a question that is a property at least you think of when you think about two sets, or two languages. So imagine I give you two languages like L1, L2, and I claim that L1 is a subset of L2. The question is, can you guarantee that if L1 is not regular, that L2 is not regular? Does that property hold? And we're going to address that here. So, to have some discussion about this, let's talk about a language called LSUM. Okay. So we're going to consider LSUM here. We're going to show that LSUM is not regular. So we're going to use contradiction as per usual in our lecture. So we're going to first assume that LSUM is regular so that we could derive a contradiction. So what does that mean? Well, now every regular language, so assume LSUM is regular. So it means that it satisfies the pumping lemma. It follows from the pumping lemma that there is a constant P that satisfies the conditions of the pumping lemma, which I'll abbreviate as PL at this stage. Now, you might be staring at this and saying, Dan, well, how am I going to deal with this condition here? So I need to pick a string that's in this language. Now, do notice how the sums work. So notice that it's K plus M is equal to L plus N. So if you notice very carefully, I can allow two of the symbols to take on no value, one from each of the groupings of these. And then I end up just getting where one of the number of symbols has to equal another number of symbols. So watch this carefully. This is how I'm actually going to pick the string. And this should remind you a lot of how I picked the string in this case. So I'm going to choose W to be 0 to the P, 1 to the P. It just looks just exactly like the one I picked before. Which has length at least P. Now you might ask, Dan, why is that the case? Why is it at LSUM? So when you get a little bit more complicated like this, a good idea to explain why. Such a W belongs to LSUM. As K is equal to P. So if you look at our constants here, so notice that, so I have K, so notice I'm using P here for the number of zeros. So that's K. K is equal to P. L is going to be equal to P. How about M and N? What are M and N going to be equal to? Can somebody tell me? What's M and N going to be equal to if I pick this string? Notice that there's no 2's, no 3's. So that means that what is M and N? What are they? They don't appear at all, right? So it's 0. So there's just 0. So M is equal to 0, n is equal to 0. And indeed, if you look at this condition here, and indeed, k plus m is equal to L plus n, right? Because m and n are 0. That means that actually all we're doing is we're checking if the number of zeros is equal to the number of ones. And if you actually look at this carefully, that's actually, those are strings that are in that language, right? But that's a whole other aside. That's because of the way we've selected the string, right? Now, by the pumping lemma, W can be divided into 3 parts, right? Into 3 parts, W is equal to X, Y, Z, where the length of XY is at most P, and of course the Y part is not empty, right? And Y is not the empty string. Now, you're going to notice I'm going to use the exact same reasoning I used when I proved that this language isn't regular. Pretty fascinating stuff, right? Because what happens? Well, if I pick my string carefully, I'm going to use k is equal to 0. So I'm going to make it so it repeats the Y part no times. Consider then string x, y to the 0, z, which is in L sum by the pumping lemma, right? That's what the pumping lemma says. That's what it... But what can we say about x, y to the 0, z? What can we say? Well, let's think about it. Well, if I take away the y part, well, what's going on with the y part? Well, what happens? Well, notice what? Notice that xy consists only of zeros. That should sound awfully familiar. So now that we were going to consider this string, well, x, y to the 0, z is equal to xz. And of course, that y part isn't empty, right? So it means it has at least one symbol. What does that mean? That implies what? So if I look at my sum of how many symbols appear, well, it means that k plus m, remember k is the number of zeros, is strictly less than the number of ones, right? As a result, I get this. But that means it's not a part of the language, right? That means that xz is not an L sum, which is a contradiction. And that completes the proof. So notice that even though that language looked a little bit more complicated than some of our previous examples, inside of it, you can actually see that the strings that I was able to expose as those for which the language wasn't regular, such as in this language, I was able to use those same exact ones in this case. Now, you might say, Dan, is this like a universal property then? So if I have L1 and L2, and L1 is a subset of L2, is it that if L1 is not regular, that L2 is not regular? Well, let's think about it. So we're going to have to be careful. So here's a question. So if L1 is not regular and L1 is a subset of L2, is L2 not regular? And unfortunately, the answer is that it depends. So in general, the answer is actually no. Now you might ask, Dan, why is the answer no? Why is the answer no if somebody gave me two arbitrary, like if you give me like if I ask this general question, why is the answer no? And this is the common question, because you think, okay, well, if all of these strings, that's a language for which I don't have a DFA, for example. Well, certainly if I have a bigger, like a language with more strings in it, it has to not be language. No, sorry, that can't be regular either, right? And unfortunately, that's not actually the most careful of reasoning, actually, because it could be the case that when you have a less specific language, that it could be the case that that is indeed regular. So let me give you a counterexample to this claim here. So that's why I'm saying the answer is no. So let's consider this. So suppose L2 is equal to sigma star. Over some alphabet sigma. So you can think of it just as 0 and 1, and then you have actually all binary strings. That's what sigma star would be in that case, if we had zeros and ones. So that would be all binary strings. Now the question, is the set of all binary strings, is that regular or not regular? Well, let's see. Let's see. So this is actually another way of me asking the following question. Is there a regular expression that describes all binary strings? And the answer is yes, there is. It looks like this.